record?
I don't record every class, but when students are out, and I knew that Miley and Savannah would be out today, so we're going to record today, all right? And of course, you can always access these as well. Okay, so we are on 12. We're at 12A. It's lab 23. If you'll turn that to that in your book right there. We're going to kind of go, remember I told you we're going to cover some specific things, i.e. the bones, the skin, the muscles. And now we're going to go back a little bit and see some of the underlying mechanisms by which all those things are powered. We have to power our muscles, right? We have to have energy supply to them. So we're going to go back and see those underlying mechanisms. All right, so here we go. Nope. Energy and life. Okay, we know this criteria. You need a pencil?
Hit her in the face. Crazy. Thank you. Yo, Ninja Star.
We know this is one of the criteria for life, right? That all life forms have to have a method by which they can extract energy from their surroundings. What did we call that?
Wait, what?
For consumers. Photosynthesis for plants. Correct. What? We call it metabolism. Remember metabolism? Yeah. All right. So the beginning of all energy comes from the sun, which is used by plants, which are then eaten by animals, which are then eaten by other animals. Okay. So the sun starts everything. Now, energy doesn't come from nowhere. Energy has to come from somewhere all the time. So if I say the energy comes from the sun, your next question should be, where does the sun get its energy? Okay, so the sun is a giant furnace, so there's a combustion reaction going on inside of the sun. We're not exactly sure what's happening, but we have a good guess. That's science, right? Making good guesses. And our good guess about this is that there hydrogen gas that is fusing with another hydrogen gas, producing helium gas. And in the process, that's called nuclear fusion. They actually fuse the middle parts of them, the nucleus of them. And in the process of doing that, energy that is already in there gets released. Which then you ask, where does the energy come from? Inside the nucleus of atoms. And so that energy is there by forces. Force is called the strong force. And the way they're attracted to one another, then we could always ask, where does that come from? So when you get to the very bottom of everything, you have to say, where is the absolute origin of energy? And really, there's only one answer. And that has to be God. It has to be, right? It's not going to come from nowhere. That's the first law of thermodynamics. Energy has to come from somewhere. It's neither created nor destroyed. It only changes form. Josh?
I've actually seen a video that like the sun could actually die.
Sure, it's burning.
No,
just
not
like
burning,
your
but
no, yeah.
But like
Just
future.
like your fire burns out when the fuel runs out.
It's
The
just-
fire in the sun, the fuel's going to run out at some
I
point.
heard it gets bigger and then it shrinks.
Yeah, so it sort of puffs up like a marshmallow, and
So
then
it might actually
deflects.
swallow mercury.
True, absolutely. Yeah, when that starts happening, we'll be in trouble too. I mean, it'll get too big, it'll burn up everything on Earth
Maybe
as well.
Mars will be in the habitable zone.
Maybe by then we'll have Mars ready to go, right? Yeah, who knows? Who knows? All right, so were you supposed to fill in that underlined word sun?
Yeah.
Okay, everybody got that? There's a blank to fill in, and you're filling in the blank with the word sun. All right. Good thing you didn't have to write all of that, right? Okay, there we go. There's our fusion going on there. Now, the sun, of course, is sending very strong radiation towards the earth. So the light and the heat coming from the sun is considered radiation. You probably heard that word and think has a negative connotation, yes? And that is true. All right, there are different kinds of radiation. And you can see that what happens is when the sun comes down and hits the earth, it has to go through our atmosphere. So here's where you see the beauty of the created atmosphere right here, because it's doing several things. One, of course, it's giving us air to breathe, right? It's also helping to maintain our temperature on the earth, okay, through weather patterns and things like this. It actually acts like a blanket. So I know we had really cold weather, and so we've talked about the problems with the electricity grid and that kind of thing. That's man-made problems, right? We didn't manage things properly and this kind of thing. We didn't know anything about that, of course. My question is, why did that weather patterns hit us out of nowhere like that? David?
Why is the sun smaller than the earth in this?
Oh, yeah, it's far away, right? Yeah, but it's way, way bigger than the earth. Yes?
Me and my mom saw on the news of the polar caps melting and forming again, like really.
When is that
Honestly.
happening, supposedly?
I think is pretty recent actually.
Yeah, okay.
The polar caps were melting a bunch.
So the idea that this weather system came straight down to Texas, it's like made a V shape, like this. So the people to our east and west were not really affected by it until it moved, of course, to the east. But the people to the west weren't really affected by it. So it's kind of strange. And of course, I have family up in Wisconsin who think we're a bunch of wimps. And we're like, no, we don't do 0. We don't do 8. I think we got down to 8 degrees. You know, that's just very unusual for us. But it turns out that the sun is warming our Earth, but we don't want it to warm our Earth too much, but we don't want it to warm it too little either. So if we look at some of the other planets, for instance, Mercury has no atmosphere whatsoever, and if you're on the dark side of Mercury, you know, the part that sun's not shining on, it is bitterly cold. If you're on the side of the planet where the sun is shining, it is steaming hot. Not even
right
steam
now.
because there's no water.
Right
You know,
in the middle.
yeah, you may have to go between to keep it just right. John,
I looked up the hottest temperature it's ever been in the world. I mean the coldest.
Coldest.
And it was negative 124 degrees.
no way.
Where?
The coldest temperature on our planet, negative how much?
124.
120. Was it like in Siberia, or was it on the South Pole or something?
I don't know where it was.
Wow.
It was in Antarctica.
Antarctica. Okay, that would make sense. Boy, I don't want to be there. Yeah, David.
I forgot what I was about to say.
Sorry, Josh.
There's this show called Snowpiercer on I think ABC, but they're on a giant train that like keeps them from freezing because the world just completely froze, and it's like minus 180 degrees.
Whew.
Yeah.
Yeah, that's no good.
But
Is
they
that
think
some
that-
sort of apocalyptic end of the world
Yeah,
type
but they
of thing?
think the world is warming up.
Oh, okay. Yeah, so I think that the world does go through patterns. David, you remember?
Yes. So up in the north, they don't experience the heat we get here in Texas.
That's true.
So 75 degrees is like extremely hot for them.
Which for us, that's winter. All right, 75 is our winter temperature. So I try to explain that like today's temperature is more like February, right? You know,
They're like,
so.
"It's hot."
All right, so what's going on then is that the sun rays are coming in, and a good portion of the very damaging radiation is actually being reflected right at the beginning, right there, through the atmosphere. There's this really cool process by which certain chemicals in the atmosphere get broken apart by the radiation, and the energy it takes to break them apart removes the energy that was put into them. You see, it kind of cancels it out. Okay, so that's called, there's UV, so ultraviolet A, ultraviolet B, and ultraviolet C. Now we talk about, have you ever used a sunscreen? And it'll say blocks against UVA and UVB, right? So, and UVC is the really bad one that gets mostly deflected out by way of the ozone layer in our atmosphere. Also, the Earth shines, the sun shines on it and it reflects it. So if you've ever seen a picture of the Earth and it looks like this pretty blue, planet, that's during daytime, because the sun's light is shining. Just like on the moon, the sun's light is reflecting off the moon. We see a full moon and at full moon time. That's the same thing with the Earth, So at nighttime, if you looked at the Earth, it would be a black sphere with maybe some lights from electricity or something like that. All right. So here we're looking at it right here. So that coming in, that UV light that does make it in, does warm the Earth, and that's a good thing. People say, oh no, global warming. No. If we didn't have this, we would be a frozen wasteland.
Like
All
my
right.
shirt.
It has, so if you were going to guess the average for the whole world, the average temperature, we have some cold places, we have some warm places, some places it's winter, some places it's summer. But any given day, can you guess the average temperature of the Earth?
60? 50.
70.
50 is correct. I was about to say, when you said 60, that's pretty good, right? So 50 is good, you might think, well, 50 seems kind of cold. It's actually pretty much perfect as an average temperature for supporting the life on the planet as we know it. All right. So keep in mind the greenhouse effect. The greenhouse effect is a good thing, and let's watch a video about it.
Alaskans in Texas is hot. Go
What
to
about
Vancouver.
that?
The greenhouse effect. When you see a beautiful, fat full moon, do you ever imagine what it'd be like to be up there, standing on its surface? Well, for one thing, hot. About 120 degrees Celsius hot.
Oh, really?
But 14 days later, at new moon, you'd be in the middle of the long lunar night, and the temperature would have plummeted to around minus 170 degrees. On average, the moon and Earth are the same distance from the sun, so they get the same amount of solar energy. But here, the average temperature is 16 degrees Celsius, while on the moon, it's more like -80. The Earth has a much smaller range of temperatures too. -88 and +57 are the lowest and highest on record. So, why the difference? The answer is the atmosphere. It protects us from a lot of the sun's energy, but also traps some that gets through so that, for example, at night, temperatures don't fall that much, especially if it's cloudy. The energy that comes from the sun is electromagnetic radiation in a broad range of wavelengths. The upper atmosphere absorbs most of these wavelengths. Visible light gets through, but a third of this reflects straight back out again, mainly off clouds and ice. So only half of the energy heading for Earth gets to warm its land and oceans. Rock, soil and water heated by visible light re-emit the energy as low-energy infrared radiation, heat. This can pass through the oxygen and nitrogen in the air. But some gases, the so-called greenhouse gases, carbon dioxide, methane, nitrous oxide, and water vapor, have molecules with structures that make them absorb the radiation. Struck by an infrared wave, they vibrate strongly before releasing the energy as a new infrared wave. This can shoot out in any direction, towards space, down to Earth, or out sideways. But in every case, there's a good chance the wave will strike another greenhouse gas molecule and change course again. Although greenhouse gases typically make up less than 1% of the air, they're in a layer of atmosphere 6 kilometers deep. Not much escaping radiation makes it through without encountering at least one greenhouse gas molecule. Over the entire planet, the result of this giant pinball game is that heat stays close to the Earth's surface for longer than it otherwise would, keeping it warmer. This is the greenhouse effect. Without it, Earth would have an average temperature of -18 degrees Celsius, which is better than the moon. But, I think you'll agree, not as good as what we've got.
All right, I calculated that, whatever that -88, the lowest temperature, and it was 126. Yeah, so you're right. Let me see if it tells me where it was. They said Vladivostok. Is that what they said on the video? Oh, it doesn't tell me here. Yeah, I just did a conversion on that. All right, so here's some vocabulary words. We have things out there, creatures, living things called producers. They're called producers because they produce their own food. They make their own food. Those are plants. So if you're going to write down an example, would be plants. If you want to write down a specific example, you could say whatever plant you can think of. Sunflower, grass, tree, yes.
So, when the people went on like the moon for the very first time, what was the moon at? Like, was it a moon? Was it a?
You know, it didn't matter. I don't know the answer to that specifically. The question is was the moon full when the astronauts landed on it in 1969 on Apollo 11? They landed on the light part of the moon. So at any given point, like if I'm looking at the moon, when it's new to us and dark on our side, the other side's completely lit up, right? Mm-hmm. Yeah. So they landed where it was light. I know that. Yeah. So they could see.
So it was hotter? Or
it was very hot. Yeah.
So do their spacesuits like make them where it doesn't?
Yes, their spacesuits are air conditioned to make it just perfect inside for them. Yeah. And furthermore, since there's no air on the moon, they have to have the pressure. On them. Yes.
Has anybody ever been to the dark side of the moon?
We have taken pictures of the dark side of the moon.
Okay.
We call it the dark side of the moon because it's never facing us. It doesn't mean it's always dark. When the moon is new, the dark side of the moon is lit up completely. It's full, but we never see it because the way it turns and the way the Earth turns, it turns just at the right rate that we never actually see that
It's
other
very
side.
easy to see the outline of it, though. Whenever it's like
when it's
half
new?
moon, when it's
Oh,
half
sure.
moon, you can still see the outlining of it.
Yeah, that's because the light from that side, like see the crescent moon, and you can still see the other side of it. That's because it's called moonshine. I know that stands for something else as well. But the Earth is the same deal. It's called Earthshine, with the other side of the Earth is visible because of the reflection going on at the Earth.
Is Darth Vader on the dark side of the moon?
I'm thinking that's where he lives, right? He's got to live there. Yes.
Can you see Earth from Mars?
You can. It's okay. So because of where the sun is, so it's like us when we're looking at Mercury. We're looking at Mercury, but the sun is on that side of it, so it looks like a silhouette. It's very hard to study Mercury, in fact, because it's so close that we're like doing this because the sun. So if I'm in Mars looking at the Earth will look like a silhouette against the sun. Does that make sense to you? Yeah. Okay. All right. Silhouette means the shadow. You know, so because if the light is behind me and you can't really see me because the light's so bright behind me, all you see is a silhouette of me. So it's not a shadow exactly, it's just a block thing. Yes, John?
I wonder if on Mars there's ever like a solar eclipse where the Earth blocks the sun.
Well, the Mars has 2 moons, so they could cause an eclipse. But I don't know. I just think the Earth's too far to do that. But it certainly could cause something. That's a good question. That might be a good research project there. All right, consumers are organisms that eat living producers and or other consumers for food. That's our other group of living things. And then we have the decomposers, organisms that use dead plants or animals for food. They decompose old stuff. So you can see them right here. We have our producers, our consumer that eats the producer. The arrow shows it goes into the mouth. So the plant goes into the mouth of the squirrel goes into the mouth of the consumer, the wolf or whatever that is, and then all of them go into the mouth, if you will, of the decomposer, which is a mushroom in that case. And that goes into the soil, and the soil then feeds the plant, so it's a nice, beautiful cycle going on there. Okay, short video here, I think.
Almost all the energy in living organisms comes from the sun. Producers use the sun's energy to make food for themselves so that they can grow and mature. Consumers eat that food.
Is that it? Very short. Okay, there we go. So what do consumers eat? Herbivores eat producers. They only eat plants. If you're a vegetarian, any vegetarians in the room? If you were, you would be considered an herbivore. Are you accusing Olivia of being a vegetarian?
Wait, but vegetarians also eat fish.
Well, they're not vegetarians, and they're pescatarians. That's a person that eats, because that's meat, because fish is meat. Carnivore eats other consumers, so only meat. So if you eat only meat, you could be considered a carnivore. I'm probably thinking most of the people in this room right now are what we call omnivores, meaning we eat both. You're an insectivore?
No.
An insectivore is a type of carnivore because an insect is considered meat.
Hey, what about the ones that eat fish? What are they called?
Pescatarians.
They
Yeah.
only eat fish?
I thought they had like some kind of.
What if someone
They eat vegetables and fish.
That's it?
That's it.
What
They're
about
called
like
pescatarians. Just fish?
Uh-huh.
Crazy? That's what, I don't know.
Wait, can herbivores eat eggs?
Insane person?
No, eggs would be considered, anything that came from an animal would be considered going into the carnivore area. That's why, have you heard of a vegan?
Yeah.
A vegan
Yes.
won't eat anything that came from a living creature, including eggs, milk, honey, because it comes from bee.
What?
Yeah, that's a
You
vegan,
didn't know
right?
that honey comes from bees?
I knew that.
Okay.
Oh my God. Wait, what about has anyone ever just
Eat what?
eaten meat like?
Oh yeah, there's a diet out there called the carnivore diet, and people like who build their muscles, bodybuilders and stuff, they go with the carnivore diet. I can't imagine that it
What
would
if someone
be.
just did meat though, like only meat and water, no milk, no cheese, just
That'd be
like
really bad,
meat
dude.
and water.
It might get boring,
You
although
have-
there's
you
lots of
have
different
really
kinds of
big
meat out
bones.
there. Okay, let's watch a video about the 3 types of consumers here: herbivores, omnivores, and
If an organism is a consumer, it can be further classified as a herbivore, a carnivore, or an omnivore. Herbivores eat only producers. Elephants, for example, are herbivores because they eat only plants, and plants are producers. Notice how an elephant eats those plants. It grabs them with its trunk and then uses the trunk to pull them into its mouth. It does this quite a lot. In the wild, an elephant spends about 3/4 of its day feeding, and during that time, it eats about 300 pounds of producers. If a consumer feeds exclusively on other consumers, it is a carnivore. This spider is an example of a carnivore. When an insect gets trapped in its web, it pounces on the insect and bites it, usually injecting a venom that kills the insect. If the spider's hungry, it might eat the insect right away, or, as this spider's doing, it might just wrap it up in more spider silk and save it for later. If a consumer eats both producers and other consumers, it is an omnivore. This grizzly bear, for example, is an omnivore. Right now you see it eating a fish, and fish are consumers, but grizzly bears also eat producers. They eat green vegetation, wild fruits, berries, nuts, and even the bulbs or roots of certain plants. In fact, producers make up about 80% of a wild grizzly bear's diet. So even though it does eat consumers, it also eats a lot of producers, and that makes it an omnivore.
Okay, and the next part, I think you skipped down a little bit for the next part on your book right there. Listen up, kids. At the bottom of the sea, there are hydrothermal vents that spew out hot chemicals into the water. And this is brought up here because they actually act like producers without going through photosynthesis. There's a process called chemosynthesis they go through. Here's where you can see some of the creatures living down there. So there is this hydrothermal vent with these bacteria that have chemosynthesis, which feed these creatures right here, which are called tube worms. They're actually worms. They're crazy looking. And some other little coral-like things like this. We'll watch a little video on this one.
This National Oceanic and Atmospheric Administration video, shot deep in the ocean, is of a hydrothermal vent. Now the smoke that you see coming out of it isn't really smoke. It's chemicals and sediment that come from deep within the Earth. You see, the Earth's interior is very hot, and when cracks form in the crust at the bottom of the ocean, the hot chemicals in the Earth's interior are exposed to the cold ocean water, forming this hydrothermal vent. Now, even though all this is very hot, you're not seeing a flame in that hydrothermal vent. You're actually seeing an illusion created by the fact that the hydrothermal vent is spewing out gas as well as liquid. So there are bubbles in the hydrothermal vent. The light that's being used to film this is actually interacting with those gas bubbles, creating what looks to be a flame, but it's really nothing but an optical illusion. Now, despite the fact that there's no flame there is a lot of energy, and that energy can support a lot of life. For example, these tube worms live on the hydrothermal vent. Now, they don't use the hydrothermal vent's energy. Instead, they house bacteria that use the hydrothermal vent's energy. In exchange for this housing, the bacteria provide food for the tube worms. The palm worm is another kind of worm that can be found on hydrothermal vents. In fact, it's not uncommon to find palm worms and tube worms living together. Now, all these worms provide food for other animals, so you find other animals near hydrothermal vents as well. For example, this is a common kind of crab that you will find feeding on the animals that live near hydrothermal vents.
Is that a robot filming that?
This crab is obviously very happy with where he's living, because when the submarine's arm tries to take a sample of the structure that he's sitting on, he actually tries to fight the submarine's arm and drive it away.
Pretty cool.
Oh, why'd they destroy his home?
Well, I don't think they realized that they were trying to get a sample to study, right? Yeah. Okay, so combustion. This is kind of our main thrust of our lesson today, y'all. Is combustion. All life forms have a method to extract energy to use it to sustain themselves. We know that is metabolism. And combustion in organisms like us, we don't have photosynthesis, right? People don't. So we go through something known as combustion, or in our case, respiration. The word is respiration. When you hear respiration, what do you think of?
A
A
respirator.
respiration mask.
And what make you think of what?
Rats.
A mask.
A mask? Oh gosh, okay. David?
What are you when you only eat decomposers?
I have no idea. Yeah.
Wait, what's wait.
Well, if you were just to eat fungi, my I don't know what that'd be called. Anyway, all right.
Would worms have
Respiration should make you think of breathing. Breathing. Okay, to respire. Okay. Here we go. This is going to be about combustion.
Combustion.
Burning.
Humans do a lot of burning. In the past, we burned a lot of wood, and we still burn some.
Listen up.
We burn huge amounts of the fossil fuels, coal, oil, and natural gas. Sometimes we burn hydrogen. Although we burn different things, in every case, the substance that we burn, the fuel, combines with oxygen in a chemical reaction that releases energy, usually heat and light, and often sound. Reactions of this type are called combustion reactions. Energy isn't the only product of combustion reactions, but usually the other products are treated as waste. For example, When we burn coal, it produces carbon dioxide as well as energy. And when we burn hydrogen, we get water as well as energy. In both of these cases, the chemical products are gases that we leave to drift off into the atmosphere. Some combustion reactions are very fast. If you mix hydrogen and oxygen gases before setting them alight, the reaction occurs in a split second. We call it an explosion rather than burning. And it's the same inside a car engine. The fuel is mixed with air in the cylinder and explodes with a spark from the spark plug. But put the same fuel in, say, a camping stove, and it burns. It's the same combustion reaction, just happening at a different rate. Combustion reactions are incredibly important for the way we live. We use them to keep warm, to heat water, to cook, to move cars, ships and planes, for manufacturing and to produce electricity. But they're not always helpful, and they can get out of control.
All right, so combustion. Yeah, we are going through combustion right now, right this minute. Your body's going through combustion. Okay, who had breakfast?
Not me.
Me.
I
had a
had
bacon.
I had a toaster strudel.
Oh,
what?
that doesn't
No, I
count.
wouldn't have had.
That doesn't
I
count.
didn't have a choice.
All right, so
Baby food.
you know that we have a temperature, right? We have a temperature.
Yes.
Not a fever, but a temperature. Or what's your temperature?
102.
I hope not.
99
98.6.
degrees.
98.6.
You said
So there's,
92.
if you're 92, you need to go to the hospital.
I think I'm like 96. I'm usually 96.
Little low? Okay, so 98.6 is normal, average. Listen up, gang. And that gives us heat, right? So that heat is being produced because we're burning something. We're burning, the combustion's going on with the food that we had. If we didn't have breakfast, the food we ate yesterday. Okay. All right, so here's our combustion equation. You're going to need to write this down somewhere. So we're going to have organic molecules plus oxygen gives me CO2 plus H2O plus energy. So the organic molecules typically are made up of carbons, hydrogens, and oxygens. There are things out there that will combust that are not made of carbon, namely magnesium will burn. It's what you have in fireworks. That's what the light is in fireworks, especially the bright white lights come from magnesium. But typically if we're burning something, I had a fire in my fireplace over this cold snap, and I was burning wood, right? So wood was made up of carbons, hydrogens, and oxygens because it came from a living thing. It came from a tree. All right, so what does combustion require? It requires fuel and oxygen. You can write O2 for oxygen if you don't want to write the whole word out. Combustion, what does it produce? It produces energy, CO2, and H2O. Okay, carbon dioxide and water. So if we're doing this right now, if I told you we're going through combustion right now, are we breathing also right now?
Yes.
Yes, so this fuel would be our food. This breathing would be our O2. So when we exhale, we are exhaling CO2 and water. That's why it's wet. Okay, when you breathe out. When you breathe on the window and it leaves steam on there, it's because we're going through this combustion. In our bodies, fortunately, it's a very gentle combustion, so we're not actually bursting into flame. All right, there's a thing out there called spontaneous human combustion where people burst into flame, but I don't believe it's true, so I don't believe it's real. Okay, so here it is, equation again in case you didn't get it. Fuel plus O2 yields, that arrow means yields or makes. This is a chemical equation just like our photosynthesis equation, which all of y'all know now, right? This is literally the opposite of the photosynthesis equation. So what is photosynthesis equation?
Energy.
6 CO2 plus 6 H2O yields C6H12O6 plus 6 O2 plus energy. No?
Are we memorizing someone's phone number?
I thought y'all knew that one.
No.
Okay, well this is the opposite of that. Photosynthesis requires CO2 and H2O to make fuel being sugar and O2. We take sugar plus oxygen to make CO2 plus H2O. In other words, we're living in a beautiful symbiotic relationship with plants.
I memorized the chemical formula for photosynthesis.
Yes?
And then I forgot it.
Oh, I don't think that's considered memorizing then, David. Okay, the last two questions on your book. Yes, something about where do we get our fuel for energy as humans? We get it from our food. And then the question for you, of course, is what kind of food makes the best energy source? We've mentioned a little bit about food earlier here. I want to tell you this story. This was one of the coolest stories at all. It's about sled dogs, okay?
Ooh, I love dogs.
My
And
cousin,
these are very cool.
my cousin got to, when she went to Colorado, they like rented it out to be able to.
To be pulled along on a sled dog through the snow? Yeah, I'm thinking it's cold, but let's check these guys out, how they can metabolize much more efficiently than we can.
Hi, this is Kate from Minute Earth.
Hi.
Humans are not the fastest mammals on the planet, but over really long distances, we can outrun every other species on land, except certain dogs. The greatest ultramarathoners on the planet are Husky Malamute mixes bred for sled racing. While pulling a load, they run 5 back-to-back marathons in a day, day after day, for more than a week. That's because of the totally unique way they turn food into energy. Like all mammals, sled dogs rely on 2 types of fuel. There's glycogen, which comes from carbs and sugar, and is quick to ignite and fast burning, like natural gas. And there's fat and protein, which come from, well, fat and protein, which are not that flammable and burn slowly, kind of like logs. Glycogen can power a runner on its own for periods of short, intense exercise, but because it burns up fast, long-distance runners rely mostly on their supply of slow-burning fats and proteins. In order to turn fats and proteins into energy, though, most mammals need to also keep burning a small but steady supply of glycogen. And that turns out to be a serious problem, because the body's glycogen storage tanks are pretty small, and converting carbs and sugars into glycogen takes a little while. So runners burn glycogen faster than they can make it. If they run for long enough, their supply will inevitably run out, and they'll bonk. Sled dogs never bonk, because early in the race, their bodies somehow shift over to burning fat and protein without needing to use any glycogen at all. And since fat and protein can be turned into energy pretty much immediately, the dogs can refuel throughout the race without ever worrying about running out of glycogen. We still don't know how this fuel burning trick works, but we do know that after 9 days and 1,000 miles through the snow and ice, most dogs finish the race with the same baseline vitals that they started with. In fact, unlike human ultra athletes who often need months to recover, the dog teams that do best in one ultra race are often the ones that have just recently returned from another one. When it comes to feats of endurance, sled dogs turn the competition to mush.
So pretty cool. I never had known that before, and so I think it's pretty cool. That's why they use those for those. Have you heard of the Iditarod race up in Alaska? That's what those long races that they go out on the sleds.
I
Yes,
guess you know
Josh.
what kind of dog you want to get lost in the snow with.
No kidding. Yeah. So, all right. So, what types of food should we eat? These?
Fat?
Yes, I love those foods.
No, those are terrible for us. Now, it doesn't mean you should never, ever, ever have a Coke in your whole life ever.
My dad is
It
like
just
me,
means I have one of my sons. Okay, 2 of my sons. One of them lives up in Arkansas because he's at school up there, and every time he orders from Sonic, I know it because it sends me an email for some reason. I'm telling you, twice a day he's ordering a Dr. Pepper at Sonic, and I'm like, oh, so that's all he's drinking. And I have another son in Austin that he drinks nothing but Dr. Pepper. I mean, no water, no coffee, no milk. Dr. Pepper at every meal, and he has had, and when he left my house, so we moved out, right? He's married, 2 kids. When he left my house, he had never had a cavity in his life because I didn't let my kids drink Cokes, mostly because I didn't want to spend money on them. But since he left my house, he's had cavities in his teeth. When I had him at home, he had not even one cavity when he lived at home. And so I look at him and tell him it's that Dr. Pepper that's doing it. So Coke in particular, I think it's terrible. It's acidic and it's sugary. He does brush his teeth, but he just drinks nothing but acid and sugar on his teeth all the time. It's terrible for you. And these other things they might have. So fats and proteins are good for us. We have fats and proteins here in this hot dog and the French fries. It's just that the type of fat and protein. If you're going to pick a fat to eat, don't pick French fries.
You know, if they didn't food color Coca-Cola, it'd be green.
Green? I thought it'd just be clear.
No, it'd be green.
Oh wow! I wonder what makes it green.
I wonder.
So let's make good fuel choices. Let's see what we have right here. Okay, here we go. Some healthier foods. For instance,
All that up.
fish. Fish is really good for you, especially wild-caught fish. I will say that now that my kids have all moved out and it's more affordable, I do buy nothing but organic produce, organic eggs, all that kind of stuff. If your mom's buying you organic stuff, yay. It's more available now, but it's also more expensive. Fresh vegetables, fresh fruits. I am a big fan of red meat, so I'm not going to go, sideways on the red meat industry. I think that's good. Maybe just not every single meal, right?
People that eat like red meat every day, though, don't they get like they're prone to like heart attacks more?
Well, yeah, they are getting more things like cholesterol and things like this, but they are getting a completed protein, which is good. You need to be able to get your completed protein. All right, so we are now going to start our lab, and we're going to be looking at combustion for the most part, okay? All right, I'm going to turn this record off.